Okay, hello and welcome back to HSDeep. We currently have our invited talk by Jiaoyang. She's currently a PhD candidate at the University of Southern California, USC, joining CMU as an assistant professor in the Robotics Institute this fall. She has received an impressive amount of awards, including a Technology Commercialization Award from the USC Stevens Center for Innovations in 2018, an Outstanding Student Paper Award from ICAPS 20, a Best System Demonstration Award from ICAPS 21, and a Best Research Assistant Award from USC in 2021. She recently led a team that won the NeurIPS 20th Flatland Challenge on railway planning and was selected to participate in Rising Stars in ECS 2021. And today she will tell us about intelligent planning for large-scale multi-agent coordination. Please.
Thank you, Michael. So let me share my screen first. Can you see my screen?
Yes.
Okay, so let me start now. So thanks for the invitation and the nice introduction. Today, I'm going to talk about multi-agent coordination, and we specifically focus on large scale. By large scale, I mean like hundreds or even thousands of agents. We are looking at how we can navigate such large teams of agents in a congested environment while providing high solution quality and robustness guarantee. Okay, so to start with, robots has now changed our daily life. People use robots in manufacturing, logistics, transportation, and we are seeing more and more robotic applications in the near future. So we have so many robots around us. One key question that we want to ask is, can we coordinate the robots to work as a team? Because in this way, they can do their own task more efficiently than before. And in many cases, they can do some new tasks that a single robot cannot do alone. However, coordinating agents is a very, very challenging problem. And it's not a problem that we need to worry about for the future. It is also a problem that people are currently facing. So take the automated warehousing as an example. So today, people have developed many different types of automated warehousing applications where we use robots to move inventory parts or goods in the warehouse so that human workers do not need to navigate in such warehouse any longer. And this kind of automated warehousing design can improve the efficiency of traditional warehouse by more than 2 times. And in many cases, they can allow people to put more inventory parts or goods in the warehouse. And as you can see here, I show some examples about different robot solutions in the warehouse. And these solutions varies from like dozens of robots in a warehouse to more than 1,000 robots in one warehouse. Take Amazon, for example, they have deployed more than 200,000 robots in their warehouse around the world. So when we put so many robots in one warehouse, it causes some issues. So here I show a simulation with 800 robots in a sorting center. The left video uses a traditional planner where every robot plans their own shortest path. And when they're going to collide with each other, we use a simple traffic route without collisions. Like one robot just wait for one time step or take a detour, just like today's road network. It's a very simple framework. It's a very robust framework, and thus is widely used in industry. But as you can see from the video, it causes serious traffic congestion when we have so many robots in one warehouse. But this issue can actually be easily addressed if we can design a more clever algorithm to coordinate the robots. So the red video shows the same simulation with 800 robots, but using one of our planners. Here we can coordinate the robots better by looking at how we should resolve the collisions more like optimally and how we can balance the traffic more evenly. And as you can see, under the same condition, there's no traffic congestion at all in the red video. And because of the difference, we look at the throughput of the warehouse, namely how many tasks you can finish per time step. There's a big difference in terms of throughput, especially when you increase the number of agents. And because of this difference, actually a good algorithm can also give us a more scalable solution in terms of the number of agents you can put in one warehouse. So motivated by this, into this talk, I'm going to talk about how we design such finder. Namely, we want to form this problem formally as multi-agent pathfinding, or MapPath for short, and introduce different techniques to solve this problem for large scale of teams, and with a focus on how we generate high quality solutions, and in many cases, solutions with theoretical guarantees. But we are not satisfied with this because we also need to worry about when we apply these solutions to real robots, how we guarantee robustness, like how we handle the different robot dynamics and how we deal with the uncertainty that can occur during execution. So we will also talk about how we combine MapPath with execution. And last, I will give you one example about Flatline Challenge, which is a real recommendation that we participate in last year and 2 years ago, and show how we combine the MapPath solver with the execution and build a system for solving this problem. Okay, let's look at the first one, large-scale multi-agent pathfinding. So we first define the problem, MapPath. In this problem, we are given an unweighted graph. And in today's talk, I will mostly use a four-neighbor grid to represent the graph. We are given a set of agents, each with a start location and a target location. We have some assumptions about the agents model. So we assume that the agents move in discretized time step, and at every time step, it can either move to a neighboring location or wait at its current location. We define two types of collisions. A vertex collision happens when two agents try to move to the same location at the same time step, and an edge collision happens when two agents try to swap their location at the same time step. So our goal is to find collision-free paths to move all the agents from their start locations to their target locations and minimize the sum of their path costs. And in our case, it's the sum of their travel times. So for example, if you look at the red figure, for this particular instance, this is an optimal solution where agent 2 wait for one time step, and then they both move to their target locations. To clarify, so in this basic formulation, we have some important assumptions. We assume this is a deterministic world, and we know the environment and know all the agents, and it is a centralized system. We will relax some of these assumptions when we move to the execution world. But for now, we have these assumptions, and even with these simplifying assumptions, this is still a very challenging problem in terms of computation. So theoretically, it is an NP-hard problem to solve optimally. And in many cases, it's also NP-hard to solve bounded suboptimally. But still, because we are interested in high quality solutions, let's still look at the problem from the optimal perspective. If we want to solve MapPath optimally, what should we do? The first straightforward idea is to use A star in the joint state space, right? So you build a root node where the locations are the start locations of the agents, right? A2 for agent 1 and B1 for agent 2. You enumerate all possible locations at time step 1. Then you do it for time step 2. And then you keep searching, following the A star logic. By the time you find a node whose locations are the goal locations of agents, you find a set of collision-free paths. And you can easily prove that that set of paths is an optimal solution. So great, we easily get an optimal solver for this problem. But let's look at its performance. So here we show the performance on a city map here. Here the x-axis is the number of agents in log scale. The y-axis is the success rate, which is a percentage of instances that we can solve within 1 minute. So as you can see, for 3 agents, great, we solve all the instances. 5 agents, we solve most of them. But for 6 agents, our success rate is 0. That means, yes, it's optimal, it's simple, but in practice, it scales very poorly. And this is not surprising because the joint state space grows exponentially in the number of agents. So what can we do here? So luckily, in 2012, people proposed another algorithm called CBS that use a decoupled idea and search the collision resolution space. So it always plan paths for each agent individually, so to avoid this exponential growth in the search space. What it does is that it first plan a short path for each agent, ignoring the collisions. And those collisions will be resolved in a lazy way in this collision resolution space. It picks a collision in the current solution and saying that one of the agents must avoid this collision. So it generates two channels, each channel with one additional constraint saying that one of the agents cannot be at location B2 at time 1. And then in the channels, it replaced the path to satisfy the added constraints, and then simply repeat the procedure, looking for new collisions, and if there are collisions, resolve them by branching. So this will give us a binary search tree in this high level. And if you perform a backfill search on this tree, by the time you find a node that has no collisions, that node provides us an optimal solution. So CBS gives us the same solution quality guarantee as A star. And here is empirical performance. The zero line is the algorithm I just described. And the green line is the improved version where if there are multiple collisions at one node, one CBS node, this algorithm makes good decision about which collision I want to resolve first. So it performs slightly better than the original CBS. And overall, now we can solve up to 150 agents, which is the great news. It scales much better than A star. But if you take a look at here, with only 4 agents, the success rate of CBS is not 100%. That means in some cases, we can solve like 100 agents. But in some cases, with only 4 agents, CBS fail to solve it within 1 minute. So there must be some special cases where CBS is really bad at, and we want to understand why this happens. So we realize that this is due to a phenomenon called collision symmetries. Here I give you one rectangle symmetry example, where I plot this twin instance 4 times. Each time I show a different combination of the shortest path of the agents. As you can see here, every agent has multiple shortest paths to its goal location. Like all of them have the same length, but all of the combination has at least one collision inside this yellow region. Therefore, actually, if you want to resolve the problem optimally or resolve the collision optimally, one of the agent has to wait for 1 time step. And this is very bad for CBS because according to the CBS logic, it has to try many combinations of this shortest path before realizing that one of the agent has to wait. So when we use CBS to solve such problem, and when we increase the size of this yellow region, as you can see here, the number of nodes CBS need to expand grows exponentially. So it becomes intractable very soon. And this can get much more complicated. So here I show a generalized rectangle symmetry. Again, the agent here, one agent moves from S1 to G1, and the blue cells here represent the location that the agent might be at when it follows one of its shortest paths. And similar thing for the agent 2, the yellow agent moves from S2 to J2. And this purple area is the overlapping area of the yellow cells and the blue cells. So when we build this in an abstract illustration, essentially what we want to do is that the blue agent want to move from this solid blue line to the dotted blue line, and the yellow agent wants to move from one of this solid yellow line to the dotted yellow line. And according to the geometry of this problem, you can easily realize that no matter which shortest path the agent pick, they always must to cross each other inside this this purple region. And whenever they cross, they visit that location at the same time step. That means all combinations of the shortest path of the 2 regions must have at least 1 collision. So this is very similar to the previous rectangle symmetry. And for the same reason, it will cause a lot of node expansions for CBS to resolve it. Therefore, our idea is as follows. Instead of like CBS, which resolve collisions by just looking at the current collision and add 1 single constraint to resolve the current collision only, we want to develop more like efficient symmetry breaking constraints to resolve collisions. So what we do here is that we say agent 1 cannot be at any location along this blue dotted border at the corresponding optimal time steps. By optimal here, I mean that the agent cannot visit those locations, follow its shortest path. It either has to wait for 1 time step, travel through the border later, or it just take a totally different path that never visits its border. And we do the same thing for agent 2. When we use these two constraints to make a branch, then we can easily show that in each child node, all the collisions are resolved because one of the agents must wait for one time step. And we can also prove in theory that this pair of constraints preserve the completeness and optimality of CBS. So here I show rectangle and general rectangle symmetry, but there also exist other types of symmetries between pairs of agents, which also cause this exponential explosion in the CBS search space. And in particular, so this rectangle symmetry, it can only happen for grid graphs because it relies on this rectangle geometry. For the generalized version, it can happen for any planar graph because we need to define this topological cross between the agents. But for this, the other four like symmetries I didn't talk in details, they can actually occur on any general graphs. And thus, so what we do here is that we design specific symmetry detection methods and also symmetry breaking constraints for each of these 6 symmetries. So now the question is that, are there other types of symmetries, or why does these 6 symmetries cover like all the symmetry exists in the MATLAB problem? So here's the experiments. We test like every pair of agents at every CBS node and see how many nodes we need to expand to resolve all collisions between them. So this figure shows that about 80% of cases, we can resolve the collisions between the pair of agents with only one node. That means there's no symmetry here in 80% case on this warehouse map. But there are some cases where we need 2 nodes, 3 nodes, 10, 100, or even more than 1,000 nodes to resolve collisions between just 2 agents. After we apply our symmetry reasoning technique, now the performance becomes better. Like about 99% cases, we resolve the collisions with only one node. And there are very, very few cases we still need more than 100 or even 1,000 nodes. So this says that the 6 symmetry we developed covers most of them, but not all of them. Let's also look at a more challenging case, a maze map. And on this map, the original CBS performs very bad. Like on average, it needs hundreds or even in many cases thousands of nodes to resolve collisions between just 2 agents. But after the symmetry reasoning, since again gets much better, like more than 90%, we resolve it with only one node. So for now, we are very happy with our method because although it does not cover all the symmetries, but it covers a very good majority of the symmetries exist in the problem. So the next question we want to ask is that, yes, we can solve the 2-agent problem very efficiently. What if we have more agents? So here I give you an example where we have 7 agents in the problem. We apply our CBS with symmetry breaking techniques. The root node here, the cost is basically the J-value, the cost of the J-value, which is a sum of cost of the shortest path of all agents, which is 2 in this case. We select a collision, for example, between agent 1, 2, resolve them with symmetry breaking. So then in the child node, there's no collisions between agent 1, 2, and longer. And thus, in this case, the cost increased by 1. We then, for example, select the left child node, another collision, resolve it, the cost increased by 1 again. So now, because we try to find the optimal solution, we have to expand the right child node. We pick a collision, resolve it, we repeat the procedure. So you realize that, wait a second, we're resolving the same collision on the different branches again and again. And each branch here actually has a slightly different combination of the constraint set. And also these collisions, like duplication, are caused by resolving collisions between different pairs of agents. So our previous symmetry reasoning techniques cannot handle this. And thus we need a new method. So how can we handle this issue? The idea here is that if we turn this high-level search into an A-star search and introduce a admissible heuristic that estimates how much the cost is going to increase on a particular node, then we can use those H values to prune a lot of search space and to avoid these collision duplications. So here's the idea. Given a CBS node and an instance, right? So we first build an edge-weighted dependency graph where each node on this graph represents an agent. And if 2 agents has a collision, we build an edge between them. And the edge weight here represents a minimum cost increase for the 2 agents exactly the minimum sum of cost increase for the two agents if we want to resolve all collisions between them. For example, here for agent 1 and 2, the attribute is 1 because to resolve the collisions, one of the agent has to wait for one time step here. And for agent 5 and 6, they travel through this narrow corridor, so one of the agent has to wait for 4 time step, and therefore their attribute is 4. Since we have our symmetry breaking techniques, all these attributes can be calculated very fast. And the next step is to solve a modified version of minimal versus cover problem. So here we want to assign a value to each node that represents a minimum cost this agent has to increase in order to resolve all these pairwise collisions. And our constraint is that every pair of nodes, the sum of their values must be at least as large as the edge weight. And we try to minimize the sum of all values. So we can prove that the minimal sum we can find is an admissible heuristic for the problem. And in this case, it's 7. So we will apply 7 back to the previous tree. As you can see, since now we have a much larger f value, we can avoid expanding many nodes and thus find the solution much faster. So let's look at some empirical performance. Here are the axis, again, number of agents, y-axis, success rate, runtime limit, 1 minute. And the yellow line is the original CBS, purple line previously by CBS. And we have heuristic and symmetry, which are the red and green lines added to the previous by CBS. And here are the results. So as you can see, on all 6 maps, both heuristics and symmetry can significantly improve the performance. And their combination, the blue line works the best. In many cases, it doubles the number of agents we can solve. And we call this best version CBSH2 RTC. So when we apply this best version to our previous benchmark map, now we can solve up to 350 agents. And more importantly, when we look at this 100% success rate line, it improves from 3 agents to 87 agents. It means this algorithm now is much more stable. And here we're talking about admissible heuristics. But if you look at the admissible heuristics, right, because we want to have these nice zero-true guarantees, we always have to underestimate the perfect heuristic. And we know that there must exist some errors, unlike our admissible heuristic is accurate, which is almost impossible to achieve. And so another idea to further improve the heuristic is that if we observe these heuristic like errors during the search and use them to modify our heuristic and generate a learned heuristic, then this heuristic can be much more accurate, much more close to the perfect heuristic. And if we use this learned heuristic to guide the search, we can find solutions much faster. But the issue here is that when we use learning, right, the heuristic is not admissible any longer, and it's even also hard to give a bound on the heuristics. So we will lose our solution quality guarantee. And that's the idea here is that, okay, maybe let's use both admissible heuristic and learned heuristic. We use admissible heuristic to maintain one open list that can provide us a lower bound on the solution quality. And we use learned heuristic to maintain another, like a copy of the open list. And use that to guide our subtraction to find solutions fast. And when we combine them together, that gives us a bounded suboptimal map algorithm. We call it the EECBS, and which is guaranteed to find a solution within a user-specified suboptimality bound. Like for example, for this brown line, we use a bound with 2%. That means every solution is guaranteed to be at most 2% worse than optimal. And with this small, like relaxed on the solution quality guarantee, now we can solve up to 1,500 agents. So up to now, we are talking about like this CBI style that like idea that explores this collision resolution space in a systematic way so that we can find good solutions while providing zero-true guarantees. But in some cases, we will look at even more large number of agents, like thousands of agents. We're also interested in like algorithms that do not like load up when we increase the number of agents. So the next idea is that we are willing to sacrifice the theoretical guarantees, but we are looking at more challenging instances. So we use an idea called large neighborhood search, or LNS for short, which is a very popular and powerful technique for solving many different combinatorial problems, especially in the constraint programming and operator research community. The idea is as follows. It's a very simple idea. So we first find a initial solution, like using whatever algorithm we have. We don't care about solution quality for now. For example, we can use a constraint programming solver here. And then we select a neighborhood, which is a subset of variables in your original problem you want to optimize using some local search idea. And then we try to optimize this neighborhood. We say re-optimize the variables you select and fix the other variables using a constraint programming solver, for example. And note that in this first step, the problem you want to solve here is usually much smaller than your original problem. And thus you can do this very fast. So you can repeat this procedure like step 2 and 3 many times, and then your solution cost will be improved over time. So this is essentially a local search algorithm, a greedy one. And we will apply this to map path, like the motivation is very straightforward. We first find the initial with an existing map path algorithm, and then we select a subset of agents. We fix the path of the other agents and we plan the path of these agents so that the results are still collision-free, and we try to reduce the sum of cost or the sum of travel times for the agents. And when we repeat step 2 and 3, our solution cost can be reduced over time. And note that here, like for the first step, we can use any non-optimal algorithm to solve the problem, like our bounding suboptimal solver, for example. And for the third step, theoretically, we can also use most of the search algorithm here, but empirically we found like product planning works the best, and that's why we use this. So this algorithm has an advantage where it depends on an existing algorithm to find the initial solution. So any improvement to existing algorithm can also improve this algorithm. And also this is an disadvantage because if we are given an instance that no existing algorithm can solve it, this algorithm cannot solve it either. So it cannot improve the scalability. But we are not happy with that. So we want to use the LS framework to also improve the scalability of the algorithm. How can we do that? We modify the framework a little bit. So if our existing algorithm cannot find a feasible solution, then we just take the infeasible solution it finds, like a set of paths that have collisions. And then we use this framework to reduce the number of collisions in the solution. So we select subset agents and we plan their paths to reduce the number of collisions. And with the collision reduced over time, by the time the collision reduced to 0, we find a feasible solution. And so if we apply this to our previous, like this benchmark map, we will get very good empirical performance. So this map-analyze algorithm can solve up to 3,800 agents within just 1 minute. And its solution quality is also very close to optimal empirically. Here we show it varies from 2% to 44%. And know that here the suboptimality is an overestimate suboptimality because we actually don't know the optimal solution here. So we just give a very conservative overestimate about how the solution quality looks like. So now we have a spectrum of algorithms where optimal ones can solve several hundred agents. The bounded suboptimal one can solve around 1,000 agents, and the suboptimal one can solve several thousand agents. So according to your application, you can pick whatever algorithm you want. But this does not solve the entire problem because remember, in the first step here, we are solving an abstract map-like problem for the multi-agent coordination problem. And when we apply it to real robots, we need to worry about the robot dynamics and also all kinds of uncertainties they are in the problem. So the second part, we will talk about how we combine map path with execution to have this kind of robustness guarantee. And in particular, I will talk about 2 models. The first one where we allow agents to talk to each other during execution, and the second one where we do not allow such things. So the first model, when we allow the agent to talk to each other so that they can update each other's progress and synchronize their progress accordingly. And in this model, we further assume that the agents will not deviate from the given path spatially. Why we have this assumption? So for example, in the warehouse, what happens is that people put the fiduciary markers, which is kind of a barcode, on the ground, and then those robots have a camera underneath, and it can scan those barcodes so that the robots can always know exactly where they locate and then adjust their locations accordingly. So in such applications, these robots can move very, very accurately in terms of the space. And also in many traffic application systems, right, those vehicles like trains, airplanes, or just vehicles on the road are navigating along the tracks or lanes, and those agents also move very actively in terms of space. But in both cases, because of dynamics, that right, the agents can move faster, slower. They can also even break down during the execution, and we need to handle this kind of dynamics. And the idea here is that we want to keep the order in which the agents visit each vertex and ignoring their preset timestamps. What does this mean? For example, we have this trillion instance, and we've got a map solution like this. We first throw away the timestamps that are also assigned to the map solution, and then we look at each location and look at how this agent visits the location. For example, this diagram means that agent 2 needs to visit location C first, and then agent 1, and then agent 2. So the agents basically talk to each other and keep the progress of each other, and then they can make their own decisions about when they move to the next location. So throughout the literature, people have developed many different models to handle agents with different dynamic requirements. And you can just deploy these algorithms so that the agents can then calculate their own like speed, acceleration, and other inputs according to their dynamic requirement. So this is a very scalable framework because we do not need to change our MapHav algorithm at all. So we can still apply the algorithm for hundreds or even thousands of agents. For example, here we have applied it to the airport operation, like surface operation project, where we focus on the San Francisco airport actually, with hundreds of airplanes, where each airplane are controlled by the pilots, of course. So they have there are a lot of uncertainties in the model, and we cannot get those uncertainties precisely during planning. And therefore, we just have a very abstract model during planning, generate a solution that minimizes the expected travel time. And then during execution, we use this ordering idea to make sure that the airplanes never collide with each other and they never end up with the loss. So in the second case, what if we cannot, what if the agents cannot talk to each other during execution? And what if the agent has very complex dynamics that they cannot follow the given path precisely? So here's the idea. Since the agents do not know each other's progress at all during during execution, right? So the best we can do is that to make sure that even the worst case happens, the agents do not collide. So we need to be very, very conservative in this case. And thus the idea here is, given a straight line segment, we first run an analysis to learn how much the agent can deviate from the given straight line, both in space and in time. So we use some control tool to get this reachability envelope that gets the maximum deviation, it's yellow region. And then we run our planner by making sure that this yellow region never overlap with each other during the planning, both in time and in space. And then we can just apply our planned path to the robots and ask the robots to follow the planned path. We know that they can deviate from the given path, but because our reachability envelope analysis, we know that even if they deviate, they will not collide with each other. It is a very conservative idea, but it is also a very general idea because it does not require any specific dynamics for the robots, and thus it can be applied to many different mobile non-autonomous robots or drones in the 3D space. But this idea also has some limitation. So because in this case, we need to modify our MapHav algorithm. Why? So first, we need to, or we prefer to pre-plan piecewise linear paths in this case, because the fewer the path segment you have, the better quality you can get eventually. So we need to replace a low-level planner to a piecewise linear path planner. This is okay, not very hard. We also need to redefine a collision. So now a collision happens when the yellow regions and two regions overlap. The collision detector here is not hard to write, but this change actually makes a high-level search much more difficult, because now we are seeing many, many new collisions. And remember the collision symmetry issue we talked about, these new collisions will introduce new symmetries to the problem. So here is an example where we focus on the temporal deviation of the problem only. So people propose this Q-bus MapHav, saying that if the agent gets delayed by at most k time step, we still want to guarantee that the agents never collide with each other. That's why in this video, every agent has a long tail that represents the potential delays of the agents. We need to make sure that both their bodies and their tails do not overlap. And because of this modification, we have new collisions, where in this case, previously it's not a collision at all, but now this is a collision because agent 2 might get delayed. And this collision actually behaves very similar to the previous rectangle symmetry, where it caused an explosion for CBS to find solutions. And if we look at this diagram basically shows now the number of nodes grows not only when we increase the yellow rectangular size, but it also increases when we increase the value of k. And also when we increase the value of k, the likelihood or the frequency of us to seeing such rectangular symmetries also increase. And that means like in this mode, after this modification, the symmetry is harder to solve and it is more frequent. It becomes more important. And similar symmetries can be found also for the large agent case where we consider the spatial deviation of the agents, right? So in this case, the agent can collide with a different vertex orbits. And such issues can happen with, for example, prime paths for drones, because drone has this downward issue. So they actually have a very long body in the vertical direction, and thus they can collide with them at different locations. And it is also a very, very common challenge when we look at robotic arms, because in this case, we use the graph is embedded in the configuration space, right? And then when you look at collisions, there are many vertices that collide with each other, because when we look at the workspace, right, the arm can easily collide with each other in those cases. So to summarize this part, we try to design MapHef solutions with robustness guarantees. And the idea is to combine MapHef with execution modules. And we talk about two modules. The first one is a very efficient one. It can solve solved agents, but it has some limitations about what type of scenarios we can apply. And the second one is a more general one, and it can be applied to many different situations. But since it requires us to change the MapHef solver, and that makes the problem harder to solve. So usually this type of solvers are not as scalable as the previous one. Okay, now let's look at the last part, where we apply these ideas to a real-way computation called Flatland Challenge, and we will build a MapHef system that solves the entire problem. So Swiss Federal Railway Company is the largest railway company in Switzerland. It operates more than 10,000 train runs every single day on a giant railway network, and its business grows rapidly. So they predict that in the next few years, they have to increase their transportation capacity by around 30%. And this is a really challenge for them because their current method may not be able to handle this. And therefore, this company collaborates with another two European companies for the competition called Flatland Challenge, and ask how we can efficiently manage dense traffic on complex railway networks. There's a competition at Euronips in 2020 that attracts more than 700 participants with more than 2,000 submissions over 4 months. In this competition, what we essentially need to do is that, given an instance like a grid map that represents the network, and we are given a team of trains with start and target stations, we need to first generate collision-free plans for the trains within 10 minutes. But then after we have the plan, the simulation starts. So we execute these plans. But as you can see, there are many cross marks in this simulation. That means that these trains can get malfunction during execution. So they may stop randomly at a random time step for a random period of time. And thus, at every time step during execution, we are given 10 seconds to fix these random stop issues and generate next action for all the trains. The objective or the reward is defined as follows, which essentially means we try to minimize the sum of travel times of all the trains and to get a small bonus when all the trains finished before a given time step. And in the computation, we are given an infinite number of instances, starting from one train on a small map to several thousands of trains on a giant map. And we are given 8 hours to solve all these instances, not all these instances, to solve as many instances as possible and try to maximize the accumulated reward. So there are three challenges in this problem. The first one is that we are asked to solve thousands of trains on a dense railway network. And second, unlike MapPath, here we are very easy to have deadlocks because trains are not allowed to move backward. So whenever you have this kind of head-on collisions, it can never be recovered. And third, like as I mentioned, there are a lot of uncertainties in this problem. And empirically, there are 100 trains that are malfunctioning at every time step in our experiments. But on the other hand, this is essentially a multi-agent pathfinding problem to apply all the previous techniques we developed and put them together into a complex, like multi-agent pathfinding based system. So the idea is the similar, right? So we have a planning phase to generate solutions that ignore all the uncertainties. And then we have an execution phase to handle the uncertainties during execution. In the planning phase, right, we have this LNS framework because we are talking about thousands of trains. That's the most scalable algorithm we have. But we further improve it by using parallel computing so that we can get solutions with higher quality. But also, since we have some offline data, we use simultaneous annealing to tune the parameter of LNS, like when you want to stop your LNS improvement. And then during execution, we have this MCP, minimum communication policies, which is one of the model in the execution model with communication, to talk to the simulator every time step and move the agents or the trains accordingly. But also we can further improve the performance because sometimes these kind of strategies are very conservative, stop the agents unnecessarily. So we use a partial replanning to fix those issues and improve the solution quality during execution. And also because the train scheduling problem is essentially an online problem, so we can actually overlapping planning with execution to generate the plans for the trains during execution, and that can improve both the runtime and the solution quality. So here's the performance. Our algorithm can essentially solve problems will vary from one agent to like up to 3,000 agents for the railway problem. And here the success rate is the percent of trains that can reach their target stations before the given time step. And in most cases here, we have 100% success rate. Only when we have very challenging instance, the success rate is not 100. But in those cases, it's usually due to the case where we have too large malfunction rate. For example, for the last instance here, like on average, there are 400 trains malfunctioning at every single time step. And that's because those like malfunction issues, it causes a lot of traffic congestion on the railway network. And also when we look at the planning time, as expected, the time grows exponentially as we increase the number of agents. But know that although here, like exactly we need 1,000 seconds, but actually most of the time was spent by the simulator, not our planner. So the planner is actually runs relatively efficient. And so this is our overall cumulative reward over 8 hours. And at the beginning, where we won this competition, so we'll compare with other solutions, we outperform the score of the second team by after 7.4 hours and the third team after 2.7 hours. And also an interesting fact is that this is a neural nets competition. And the competition is branded as multi-agent reinforced learning. So actually 2/3 of the team participate in this competition using learning methods. And when we compare our solution with the learning methods, we're actually way better. So here I show that we reach a score of the best learning method after only 15 minutes. And the organizers also did detailed comparison between our method, these blue points, with the top learning methods, like with a much longer runtime limit, like here 90 hours. And as you can see here, we have better success rate on almost every instance, and also within the same runtime limit with some more instance than the learning methods. So here's a street example to give you a feeling about why our solution is better. So the left video is a batch reinforced learning approach. This is our solution. And for the same instance, this is our solution. So very straightforward feeling is that we can handle much more than like traffic density than the learning method. And that's the reason why we can move the trains to the destination much faster. And so here is just a summary of the overall performance. Like we saw 363 instance overall with a like the highest reward per instance compared to other solutions. And this is for New Year 2020. So last year they have a new edition called Flatland 3 that makes some new features to the problem. Some very interesting one, like the trains now have a time window, like a timetable about when they can depart and when they should arrive. And the trains can also move with different speeds. And also make some modification about the setup, like a smaller runtime limit with a fixed number of instances we have. And so for us, these new features are easy to be taken into consider because we just need to modify our LNS in the low-level search and also in the objective to account for those new changes in the agents. And also one improvement here is that we realize that we can also use the LNS still in the replanning phase. That means during execution, we can also continue to run our LNS to improve solution quality. So when we combine these two together, we again have the highest solution in the computation. This time we actually solve all instances given to us and with some like seconds even left. and also in this case, actually, because of all those time windows and the speed like constraints, the problem actually each instance becomes much challenging. So for example, in this computation, in this edition, the best learning method even has trouble to generate acceptable solution quality. Like their solutions are terminated because of the really bad solution quality. Okay, to summarize, we first talk about a different algorithm for solving multi-agent pathfinding problem scalably and with high quality. And then we talk about how to handle the robustness issues by combining MapPath with different execution modules. And last, we give you an example about this Flatland challenge that combine the two together into a uniform like system. So before I stop, I want to give like credits to all my collaborators because these are all the work in the really like a joint like effort among all of us. And also I want to thank everyone for coming and listening to my talk. I'm happy to take any questions. And before I finish, just one more sentence. So like Sven colleague, my advisor, will also give a talk on MapPath in the main conference with a focus more on the like different algorithms and there are other types of applications. So feel free to join his talk as well. Thank you.
Thank you. That was very inspiring talk. Thank you. We have time for questions. Anyone? I can ask a few questions. Very interesting work. I'm interested in the theoretical part of that work, in the first, I guess, part. And I was wondering whether some some ideas from classical planning can be brought here beyond heuristics, right? Like pruning techniques from classical planning, like symmetry detection and the partial order reduction. And symmetries in classical planning are slightly different from what you mean by symmetries here, I guess. And can you talk a little bit about that?
Oh, yeah. So actually, the heuristic idea here was originally motivated by those like cost partitioning idea where you focus on like subset of problems, right? And then you get, like in our case, we get heuristic for pairs of agents, like the cost for pairs of agents. And then we develop ways to combine them together and generate like better ones instead of just add them up. And so that's actually how we develop heuristics. And also for symmetry, yes. So we have looked at like methods like other than like our manually designed like symmetry breaking techniques. So for example, we have looked at a technique that we can combine mutex propagation with our like symmetry issues that, and in that way we can actually find all the symmetries I show in the slides autonomously, like without like we need to look at them, right? So the algorithm can find it for us autonomously, and thus can cover actually all symmetry in those cases. Although there's a trade-off because when you apply those type of fancy techniques, it has a big overlap. And so sometimes it gives us better solutions, but sometimes it's actually slower than what we have. And in terms of other like techniques, I'm always very interested in like coding techniques and others. But to me, like one special like property of this CBS search or this collision resolution space is that there's very few duplicates in the search space. Like we are doing a binary tree search, and this is because it's very unlikely for us to visit the same state twice. I mean, theoretically, yes, but in practice, it's very likely to happen, and that's it makes us harder to think about like how we can say merge some nodes, or we can say point some nodes using the previous knowledge. But I think it is definitely an interesting like direction, and we can think about more about how we further make use of this kind of techniques.
Thank you. Anyone else? Just raise your hand. Yeah, Wheeler.
Awesome talk. I'm wondering whether you think that MapF has lessons for sort of more general like task and motion planning type problems where there are, again, two levels of planning going on, but they have a different character than they do here. What are the lessons that MapF can teach us about other kinds of optimization problems, do you think?
Yes, so that's a very good question. So I think I can understand it from two perspectives. So on the one hand, so what MapF tries to solve is a problem where the agents have competing results. Like in this case, the competing results is a space-time like position, right? So and thus, so people have looked at like whether we can apply this CBI style algorithm to other problems, like for example, two task planning problem where agents are competing for the same tasks. So there are some work on that, and there are even some work to look at, I don't know, like the other types of problem like network routing, like pipe routing style problem. So and there's always a trade-off, because if you think about the joint state-based search, like A-star search, that's like the traditional method where you do task planning, where you have all the agents, all the tasks, and you reason about all combinations. And what CBS tries to do is that you first assign those tasks first, and then you try to address all those conflicting assignments. So, and from the lesson we learned here, so it really depends, like which one works better really depends on how, like in which way the problem are coupled. Like in the MapF world, right? Like in most cases, we can find shortest paths with not. Let me take this back. So so finding paths without collisions, like the frequency of the collision happening is really smaller than the size of joint space. That's why CBS runs faster, although like the collision resolution space is still exposed to the large space. And so the similar thing applied to the task planning world. So it depends on how your tasks are formulated, and then we can do the thing separately or use the different methods. So that's one way. And another way is that people do look at whether we can use the CBS style algorithm to solve task and task planning together. And just one nice property here is that we say MapF is a problem, but actually it is polynomial time solvable if the agents are interchangeable. So if the goal locations are interchangeable. And this can happen in many applications where you combine task and task planning, because if all the agents are identical, right, you just need to move them to some design locations, and you don't care about which one moves to which location. And that actually makes the problem easier. So then you can combine task and task planning with very nice property with polynomial time. And also if you have team of agents, you can use CBS style algorithm with that polynomial time algorithm together. Then you can do task and task planning together. That actually runs even faster, like makes the problem even easier to solve than the original MapF problem. So that's another way to look at the combination of task and task planning.
Okay, thank you. Anyone else? We still have some time. Okay, good. Let's thank the speaker.
I'm happy.
Oh,
Can I
yeah.
can I just if no one else
Yeah.
has a question, I of course am dying to hear about like whether any of this technology is actually going to get used by Amazon or the Swiss Railway or any of that. Like I would love to hear about some of this stuff actually making it out into deployment, or at least inspiring some stuff that gets deployed. And you've done so many cool applications. What can you tell us about how this work is inspiring actual industrial use?
Yeah, so I think in terms of the warehouse applications, there are like many like interests there, because nowadays automation, like as their business grows, they run more and more robots in their system. And traditionally they use this traffic system, like the single planner I showed at the beginning, and the number of agents they need is on the left side, right? So they are happy with the current method, but now they are facing more and more such challenges. So for example, what I learned from Amazon is that they are currently using the traffic system, but they are very interested to look, say, how can we move from the traffic system to the search-based system? Maybe the first attempt is a combination of them and see how they perform, and then we can slightly move to more search-based methods so that we can handle more agents. And for the railway company, the Switzerland railway company, so honestly, I don't know, because so the story behind that, they designed that competition is to look for novel learning methods. That's their original motivation. And with John, that competition basically saying, no, like the planning methods are much better. You should think about like clever planning method or clever scheduling method instead of just looking a pure learning method from scratch. So we are trying to convince them now, but I don't know like how they are going to move from there.
Thank you so much.
Thank you.
Santi?
Hi, I was just wondering, you mentioned that when you were doing the flatland problems, the simulator was really slow, like 70% of the runtime was using the simulator. If the simulator for the next edition is like 10 or 100 times faster, would it make a big difference for you compared to reinforcement learning methods, or the same? Do you have any thought about that? Like, did it help you or did it hurt you that the simulator was so slow?
So there's a trade-off. So on the one hand, like for example, we run the algorithm for 8 hours or something, right? 2 hours in the second edition. If the simulation is faster, then we can look at even more challenge instance. And as we can see from the result of this 90-hour experiments, the more challenging instance we have, the larger the difference in terms of success rate. So in that sense, like we will have more advantages over the learning method. But on the other hand, in terms of the runtime, I actually don't know, because so there are two reasons why we run even faster than the learning method, which is kind of counterintuitive because learning method just is a policy-based method, right? So well, there are, of course, one reason is that those learning methods have like deep network, and even for their test time to generate the policy, it takes time. But on the other hand, because of simulation is so slow, the worse the solution code you have. That means the longer the make span you need. And that means the longer you need to run your simulation. So so that's I would say very unrealistic features in the competition, but that is what we face. So we realize that the better solution quality we have, like the more time we spend on planning, in some cases, in the end, we spend overall less time in simulation. I mean, the overall less time total runtime.
Thank you. Great talk.
Thank you.
Okay. Let's unless there are another last minute question, let's thank the speaker again. It was wonderful talk. Thank you so much.
Thank you. Thank you, everyone.
And we are adjourned for another break of 20 minutes. After which we will have the third session as usual, we are leaving the Zoom meeting running.